Hi, the lecture today is about antiderivatives. In your calculus class so far you have been learning about differentiation. So you take a function and then you find its derivative. So for example, if you have a function f of x is equal to x cubed, you learn about the process you go through to find the derivative of this with respect to x, and that derivative is 3x squared. What we want to learn today is how about reversing this process. If I have the derivative given to me, can I find the function that gave birth to it? This process is referred to as anti-differentiation. So anti-differentiation will try to undo the damage we have been learning to inflict upon a function. So if I have given a function, say g of x equal to x to the power of 4, we try to find a function. We don't know what it is yet. We try to find a function that if we differentiate it, we are going to get x4. So pause for a moment and ask yourself, what is such a function? From all the practices you have done, you should be able to figure out something. Well, when you are differentiating a function, you learn that the exponent is reduced by 1 and the exponent becomes a multiple in front of the term you had. So we have to undo these two steps. The original function has to have a power that is 1 higher than this. So let's start with that. If I have the power x to power 5 and differentiate that, do I get just x4? Well, not yet. I'll get really 5x to power 4. What if I just want to have x to power of 4 itself? Well, you have learned that if you take this function and divide it by something, then its derivative will also be divided by that number. If I want to get rid of this 5 here, I might as well just divide by 5 on both sides and I'll get the function that I'm looking for. So the function whose derivative is x to the power of 4 seems to be x to the power of 5 over 5. Except for one tiny problem. If I had any constant in my function, any constant such as say number 17, if I have a constant here and I differentiate, I still get x to the power of 4 because the derivative of that constant is just 0. It doesn't matter what constant I have here, same thing is going to happen. Excuse me. So here is the notation that we are going to adopt. If I have a function g of x that is given to me as x to the power of 4, I want to indicate its antiderivative, and our elementary notation would be to use a capital letter corresponding to the name of this function, and you write capital G of x, and that's going to be the function that if I differentiate, I'm going to get this thing back, and that function we learned is x to the power of 5 over 5 plus any constant. To indicate an arbitrary constant, we typically use letters like C, K, or any of these. And what we have in mind is to go ahead and practice this, learn a few things about anti-differentiation. Let's first just try some functions before we go on to a bit of a theory. I write down a few functions and ask you to pause for a moment and try to find out for yourself what the antiderivative is. Suppose I write h of x equal to x squared. What is the antiderivative? First of all, what letter should I use to call it by? So what it is, capital H of x, and what is the function itself? Well, we increase the exponent and divide by the new exponent and just add some constant. Let's try one more. Suppose I write say L of x is equal to square root of x. So what would be the name of antiderivative? Antiderivative of this is going to be called capital L of x. And what is that? Well, to prepare this thing, we write it in the exponent notation, x to the power of 1/2. And just as we learned here, we have to take that exponent, increase it by 1 notch, divide by the new exponent, and add some constant to it. Since these things are not related to each other, I could reuse these letters, but if the problem was connected, I had to be more careful. Let's go ahead and clean this up, see what happens. So L of x is equal to x to the power of, this is 3/2 over 3/2 plus a constant. You write the reciprocal of this fraction, 2/3 of x to the power of 3/2 plus a constant. If you wish, you can write this thing with radical notation. Now let's go ahead and combine some of our functions. Suppose I have a function and call it a of x, and that is 5x squared minus 7x to the power of 9. Antiderivative of this is going to be, let's write it capital A of x. If a function is made out of sum or difference of functions whose antiderivative we already know, our job is going to be really easy. We just take these individual functions and write their antiderivatives, multiply by the constants that they already come with. So for example, I look at x squared, its antiderivative is x cubed over 3, and since it was multiplied by 5 here, I just multiplied by 5 here as well. X to the power of 9 has an antiderivative of x to the power of 10 over 10, and since it was being multiplied by minus 7 here, I do the same thing here. And now comes the issue of constant. You might think that you need one constant here for and another constant for the other one, but really you can combine all the constants and just write it as a single constant. So I just write single c. Let's go ahead and make sure we don't commit one of the very common mistakes at this level. A mistake that parallels a similar mistake in differentiation itself. Suppose I have a product of two functions, such as just say x squared and x cubed. I picked two very simple functions. We are multiplying these functions. Let's for a moment imagine that we don't notice that you can combine these two. Just leave them as it is. Suppose I want to find the antiderivative. Would it be correct to go ahead and take the antiderivative of this one and the antiderivative of that one and multiply them with each other? That is, would it be correct to take x squared, take antiderivative and write x cubed over 3, and the other one x to the power of 4 over 4, and whatever you want to do with the constants doesn't matter, because this is not quite kosher. Let's see what is the problem here. We know for sure that if we had remembered to multiply these two functions, the function would have been x to the power of 5. So if b, I write it as x to the power of 5, then capital B would be x to the power of 6 over 6 plus whatever constant you wish. Obviously this has nothing to do with that. This is x to the power of 7, denominator is a 12, and there is no way of reconciling these two with each other. So before we go too deep into this topic, let's be careful about one thing. We have a simple rule for anti-differentiation, which is just a copy of its rule for differentiation. If several functions are multiplied by some constants and then they are added and subtracted, you can anti-differentiate each of them individually and multiply by the same constants and add or subtract exactly the way you had them in the original function. But this is only good for addition and subtraction of functions. It doesn't go where you want it to go. It doesn't work for multiplication, division, or powers, or any of those. So let me put a big danger sign right next to this. Maybe I make it big, bright red color here. Here's a big danger sign. If you have a product of two functions, you cannot anti-differentiate them individually and then try to make something out of that. Life would be too simple and uninteresting if that were true. It just doesn't apply. So in this case, well, you had the luxury of actually being able to multiply these two with each other. Later on we come across problems where it is not as easy. So for example, if you have x times sine of x, there is no way of condensing them into something and then proceeding from there. We have to find other ways of finding antiderivative. But for now, let's go ahead and practice some of our basic functions and make sure that we know antiderivatives of some elementary cases. First formula that we have, first one that we have talked about today is the case of power function. If I have a function f of x being x to the power of n, then the antiderivative of this from the exercises we just went through is obtained by increasing the exponent by one notch and dividing by that new exponent and then adding a constant. And what we are doing here, n is considered a constant. N could be 2, 3, or 5, or minus 10, or radical 2, or any of these things, so long as it is constant. Constant means it doesn't depend on this x. Well, that's one thing we have to be careful about. It's going to cause us problems later on. This n should be truly a constant. Second thing, there is something a bit problematic about this answer that we are writing. Whenever we write a fraction, we got to guard against dividing by 0. When would it be that we would divide by 0 here? Well, if n was minus 1, this expression would not make any sense at all. So our next example is to look at the function x to the power of minus 1, better known as 1 over x. What's the antiderivative of this function? Well, antiderivative of this function, a couple of months ago you have seen that this is just a natural log of x plus a constant. There is still something to be careful about here. This x could be either positive or negative, but you know that logarithm of x has a restriction on its domain. Its input cannot be negative number. You can check easily check to see that logarithm of x and logarithm of minus x, both of them have the same derivative. So to indicate that fact and to have one formula that covers all the cases, we sometimes write this thing as a logarithm of absolute value of x. In many examples, you'll see that x is going to be taken to be a positive number, so that our expression is not going to become too complicated and cumbersome, but the correct answer has an absolute value in it. Our next example is exponential of x. Exponential of x, that has the easiest antiderivative. What's the antiderivative of exponential? Well, you have to remember that the function that you differentiate and it gives you exponential of x, which function is that? And that is obviously just a copy of that original function to which we are adding some constant. These are some of the very basic functions. Now let's go ahead, take a quick look at the trig functions. If I have, let me just use the letter F all the time because we are going to gradually run out of letters. Cosine of x. What's the antiderivative of this? Okay, let me pause for a moment and let you think about it, and also make sure you got the correct plus or minus in your formula. And so what is that? Antiderivative of cosine of x is just sine of x. Why? Because if you differentiate sine, you're just going to get cosine. Another example, if you have sine of x, then your antiderivative, now go ahead and figure this one out. What function should I write here so that when you differentiate, you're going to get sine? Obviously, this is the other function, cosine. But if you differentiate cosine, you're going to get negative sine. So I need to compensate by putting a minus here, and then I'll be correct. What's another basic example we have seen? That would be f of x equal to secant square of x. Antiderivative of that one, do you remember what was the antiderivative? So this section is going to become heavily memory reliant. You need to know a long list of formulas and their derivatives to be able to go backward, and that's just to get started. Perhaps you enjoy this kind of problems. The function whose derivative is secant squared is tangent. So another example that we have, of course, that would be cosecant square of x, and I'm sure you remember what was the function there. You just need to remember the correct sign. And I hope when I am talking about sign, from the context you can tell the difference between this plus or minus I'm talking about, or actually the trig function sign. So we are going to have a bit of a hard time distinguishing between these two words, but from the context it might be clear. And sometimes instead of using this word I just say plus or minus. Okay, the answer here of course is minus cotangent of x. And another example we have f of x being secant of x tangent of x, and antiderivative of this, do you remember the function whose derivative is secant tangent? Your work is cut for you. You have to go back and memorize all of those things all over again. And you notice it's a little bit unsettling here that these formulas coming out of thin air, and we essentially don't have much of anything better than just memorizing them. And that's going to be the flavor of topic for quite a while at the beginning of Calculus 2. You are going to spend a lot of time going from a function to its antiderivative, and that's going to become a hobby of yours. But right now I'm just laying the foundation. Let's just write one more. If you have cosecant cotangent of x, then antiderivative of it is minus cosecant of x. Now if you go and collect all of the formulas you have seen, actually you are going to make a very long table, perhaps a couple of dozen items long, but some of them are a little bit more important than some other ones. Among the important ones is this one, 1 over 1 plus x squared. What was the antiderivative of that? You like to pause for a moment and come back and tell me if you recalled it in your memory. This is tangent inverse of x. We gradually will be in a situation that we would need to really understand all these trig functions and how to manipulate them, as well as how to manipulate these type of quadratics that you have seen in your college algebra classes a lot. So a lot of algebra and a lot of trigonometry that you have gone through, hopefully you have gone through, is going to be here to create a bit of a challenge for you. So make sure you go back to some of these items as soon as you need them, and don't let it just sit there. Now, sometimes for the same formula you can have several antiderivative. For example, it can be tangent inverse, can be minus cotangent inverse, and so on. Let's just stick to some of the familiar ones. Another function that we are going to see very often is this particular function. These are here f of x. Do you remember the function whose antiderivative is this peculiar expression 1 over radical 1 minus x squared? You're right, this is sine inverse of x plus a constant, or you could write it as minus cosine inverse of x plus a constant. There's still a lot more of these things you have seen on the section on trigonometry, and you can go back and check each of them. Let's mention one application of this anti-differentiation we are beginning to learn. Application. Well, we can imagine any application we have mentioned on the section on differentiation has a reverse application, which will be in the section of anti-differentiation. For example, do you remember that if you had the position of a particle, suppose S is the position, as a function of time, let's indicate that t is some time. So S, by S we mean S as a function of time is given to us by some formula, such as those famous 16t squared and plus 32t and so on. Okay, how would you get the velocity? A particle that moves is going to have some sort of a velocity, and that velocity comes from its position. What do you do to the position to get the velocity? You're right, you have to take a derivative of position with respect to time to get your velocity. So that's your velocity. You can go one notch further. You can go ahead and find out the acceleration. Here you can take the velocity itself and look at how fast it changes, and then you're going to get acceleration. So from S to V to A, in each instance we differentiate it. So one derivative brings S to V, another derivative brings V to A. You can imagine that in some situation the velocity might be given to you. Like you look at your dashboard and you can read the velocity, but perhaps you don't know where you are. You can use your velocity to figure out your position. That would be a reverse process, going from velocity, information from velocity, to information about the position. That would be an application of anti-differentiation. Similarly, if you have acceleration, if you know what is the acceleration of your vehicle and you want to find the velocity, it's very simple. You just have to find the antiderivative of it. So going up is an example of anti-differentiation. And then going downward, that was an example of differentiation. The topic that talks about this kind of things is either mechanics or dynamics. Here is typically referred to as rectilinear motion. Rectilinear is a fancy name for describing a motion that is very simple. It simply means that you're staying on a line, you are going straight. That's all it means. So if you are constrained to stay on a straight line and you are free to travel in whatever manner you wish, to the right, to the left, backing up and accelerating or decelerating or whatever, that type of a motion is called a rectilinear motion. This type of problems have components like this. Some of these information might be given and you might be asked for some other components. Let's go ahead and practice a simple example of a rectilinear motion. When we talk about this type of a physical application, some physical terminology will come in. For example, we have a concept of initial position, which just means that at the beginning of time, at time t equal to 0, exactly what is your location? It's called initial position. Similarly, there's a concept of initial velocity. Like, for example, if you are holding a ball in your hand and then you throw it to pass it to somebody else, at that very first moment, how fast were you throwing that ball? That's going to be initial velocity. The location of your hand will be initial position. Now, rectilinear motion could happen in any direction so long as in a straight line. So it could just as well be on a vertical line. Typically, your movements are either happening on the x-axis or on the y-axis, but it could be along any line. It does not matter. Here, let's go ahead and take some examples and see how we handle this. Suppose we are given that, so here's an example. Suppose we are given that the acceleration of an object at some time t is equal to 5t plus 1. Its velocity at time 0 is given to us at, say, 3. Its position at time 0 perhaps is given to us at -1. Question: find velocity and position. Okay. Remember, we said the v is antiderivative of a. So I take this 5t plus 1. This is my function. That is going to give me my antiderivative. What's the antiderivative? Here we are deviating from that notation we just developed. These guys, each of them have a letter associated with themselves from the topic. So instead of using the math notation, we use the physics notation that comes with them. So this is going to be velocity. What am I supposed to do is I'm supposed to take antiderivative of this. Antiderivative of t is t squared over 2. I had a multiplier of 5, I still have it. Antiderivative of 1, well, that's just t itself. And then I have some constant. Now, who is my constant here? We go back here and say that problem comes with additional information. For example, I'm given initial velocity. Let's go ahead and enforce the initial velocity information and see what does that tell me. V at time 0 is going to be 5 times 0 plus 0 plus c. V at time 0 is supposed to be 3, so that tells me c is equal to 3. So in this simple problem, that constant of integration turned out to be that initial velocity. It's not always this straightforward. Sometimes it might take longer to figure out what that constant is. Now I have that was the acceleration. Now I have the velocity. Velocity is determined as 5/2 of t squared plus t plus, now c turned out to be 3. My next step is to find out what the position is. So position is letter s. S is a function of t. I have to take antiderivative of this. T squared becomes t cubed. Now I have to divide this by 3, so that makes it 5/6. T becomes t squared over 2. 3 becomes 3t. And then again I need a constant. I might use the same letter, but in order to prevent confusion I just use the same letter, a different letter. Once again, s at time 0 is given to me to be -1. That's the initial position. I go ahead and use it here. I plug 0, this becomes 0, plus 0, plus 0, plus k. All of that is supposed to be -1. So I go ahead and just write -1. So that tells me that the constant k for this section of the problem is -1. That's going to determine the position for me. Position is going to be this formula with k replaced by its now given value. This is 5/6 of t cubed plus t squared over 2 plus 3t plus, now k turned out to be -1, so it became -1. The combination of initial position and initial velocity sometimes is referred to as initial conditions. We are going to hear a lot more about this after you have taken all of your calculus classes. You'll be required to take a differential equation class, and there would be a lot of material similar to this section but expanded to the point that it becomes all a course by itself. Right now we're just staying at the beginning level. Now you want to go ahead and do as many problems from this section as you can to just get the knack of it and make sure that you correct some of those common mistakes that the student commit. Maybe go ahead and do a couple of examples so that you see some of the tricks of the trade. There are truly so many non-trivial problems in this section. Anti-differentiation is totally unlike differentiation. For differentiation, all you needed to know was like excuse me, half a dozen rules and some special functions, and you are essentially all set. But for anti-differentiation, there is never an end to the topic. It doesn't matter how many cases you have studied so far, there can be always another one that would be challenging. For most part, you are not going to be dealing with those challenging cases in Calculus 1, but in Calculus 2 you are going to get a handful of those type of problems. Let's go ahead and answer some question here. The problem could be posed in a variety of languages. Here I use the following language. It might tell you that f prime of x is given. For example, that could be, say, radical x times 6 plus 5x. Some initial information might be given to you about the function. For example, it might say f of 1 is equal to 10. Objective is to find the function f. Who is f? Okay, what mistake is it that we are not going to make here? You remember I mentioned that you cannot take these functions that are being multiplied, anti-differentiate them separately, and multiply later. Whatever multiplication you want to do, if there is anything to be done, it has to be done up front, not at the end. So here we write f prime of x. I just go ahead multiply. To get myself ready, I also write it in exponent notation. So instead of radical x, I wrote x to the power of 1/2 plus 5x to the power of, this is 1, that's a half, makes 3/2. So the trick here simply was to do the algebra first. If you can do it first, and then go ahead and proceed and do whatever you want to do. Well, what is it we want to do? We want to anti-differentiate, and here is 6. Exponent 1/2 is supposed to go up 1 notch, so that makes it 3/2. That gets divided by 3/2. 5. 3/2 is supposed to go up, it becomes 5/2, and we have to divide by that exponent. And then we have some constant. How are we going to nail this this constant? That initial condition is going to be used to nail that down. Let's go ahead and clean up some. F of x, this is 2 times 6 over 3, that makes 4. And here 2 times 5 over 5, that's just 2. So that's our function. The only thing that hasn't been determined is f of 1 has been set at 10. Initial conditions are usually specified at 0 to imitate physical situations where time starts at 0 or your experiment starts at 0, but it doesn't have to be. It could be given at any location. For example, here f of 1 is given. So if f of 1 is given, I go ahead, see from this formula, f of 1 is going to be 4 times 1 to the power of 3/2, which is just 1, 2, 1 to the power of 5/2, that's just 1, and the constant. F of 1 was supposed to be 10, so we want this to boil down to 10. That tells me simply c has to be, this is 6 of 10, the c has to be 4. That finalizes my problem for me. F of x is 4x to the power of 3/2 plus 2x to the power of 5/2, and now c turned out to be 4. Okay, here's another example with a different point to it. This is, for example, that f of x is equal to x squared plus x plus 1 over x. Now we are going back to our other notation. Question is, what is capital F, the antiderivative of this one? Okay, here is a typical dangerous problem. Dangerous because we think of a certain rules which simply don't apply. They are just very comfortable. Everything will be nice if they were true. It's not true. Now, what is the dangerous thing? Dangerous thing is to think that you can take the numerator and anti-differentiate that. That is, write something like x cubed over 3, anti-differentiate x, that's x squared over 2, anti-differentiate 1, get an x. Perhaps add a constant, perhaps even forget that one. Go ahead and do the same thing in the denominator, and perhaps you want to add a constant or you want to add later or whatever. It doesn't matter because they are all incorrect. You simply cannot do these things in this order. The only easy rule that we had, let me just emphasize that, let me take you to the beginning of this. The only case where you can do something simple like that is when you have two functions added or subtracted or multiplied by some numbers. Then you can take them individually and anti-differentiate them and then add and subtract later. That is, you can exchange the order of things you want to do. But that's the last of the easy situations. Anything after that is not going to follow such simplistic rule. If you have two functions multiplied, you cannot go and take antiderivative of this, antiderivative of that one, and expect anything reasonable. Similarly here, if you have a ratio, it is very tempting to think that you can go ahead and take antiderivative of numerator, take antiderivative of denominator, and expect something correct to come out of it. It just doesn't work like that, and nothing could be further from truth. So try as much as you can to push that out of your mind. Well, if that's not something legitimate, what can we do here? We haven't seen any function like this so far, or any function whose derivative will be like this. Okay, that's where familiarity with topic comes in, and you are going to learn a long list of tools you can apply to make your functions behave and give you your antiderivative. Here is very easy. You have to just apply algebra. Algebra meaning you can break up your fraction. That's a very simple rule, and it's very useful. You're going to see a lot of it. What do we mean by breaking up a fraction? If you have a fraction, several items in numerator, and then you have one common denominator here, you can break it up in individual fractions. Well, what's the advantage of that? Advantage is that these expressions might be easier for you to handle than the whole big one. So we are going to have a huge variety of so-called partial fraction decomposition, breaking something apart into pieces. This is one of the simplest types. So what do we do? Let's go ahead, make ourselves some room here. We take this function x squared plus x plus 1 over x. We break it up. X squared over x plus x over x plus 1 over x. Okay, we did this thing because we were wishing for some simplification. So once it happens, let's make use of it. X squared over x is just x. X over x is just 1. This guy doesn't simplify. Now we have obtained three separate functions that fall in the category of things we have seen. So what's the antiderivative of x? Antiderivative of x, here I write x squared over 2. Antiderivative of 1. One function is it that if I differentiate, I get 1. That's obviously x. This one was a bit trickier. But function whose derivative is 1 over x. You remember that was natural log of, to be precise, has to be absolute value, natural log of x, and then you throw in a constant for good measure. So that is one example, and as you do problems here, you will see other tricks that you will learn. Let me go ahead and ask you to go and review these problems, and we end up this lecture at this point. Good luck and God bless.